A teenage girl is pulling her little brother on a sled up a snow-covered hill. He has a mass of 30 kilograms and she has a mass of 59 kilograms. The angle of incline of the hill is 11 degrees. She pulls on a rope attached to the sled and pulls at an angle of 40 degrees relative to the surface of the hill. She pulls him at a constant speed. The coefficient of kinetic friction between the sled and the snow is 0.15, and the coefficient of static friction between the sled and the snow is 0.18. What is the tension in the rope? This problem is going to focus on practice with Newton's second law. We'll also get practice tilting the XY axes, and we'll also get practice solving a system of equations. Let's start by drawing a picture. If there's no picture included, that's always a good first step to begin. I'm going to keep it really simple and just draw the hill. And then I'm going to represent the boy in the sled as just an object here. We don't need a lot of detail there. And then the rope, and that's being held by the girl. We don't need too many details there either. Now let's draw a free body diagram for the boy in the sled, because we want to solve for this tension in the rope. And if we draw a free body diagram for the boy, that's going to include that tension force. So let's draw that free body diagram. We represent our object as a dot here. We have the weight pointing down, the weight of the boy. We have the normal force, which is always perpendicular to the surface. We have the tension in the rope, that is just in the direction in which it's being pulled. And we have the frictional force, which is parallel to the surface and opposite the direction of motion. Now the question is this a static friction or a kinetic friction? Because he is being pulled, he is in motion relative to the surface, this is kinetic friction. Just because we were given both the information for kinetic and static friction does not mean we are necessarily using both. We just need to use what's relevant. Now let's look at our choice of axes. If we choose the traditional XY axes, like this, we would then have three forces that have both X and Y components, and only the weight would just be in the Y direction. If instead we use XY axes that are tilted like this, we now have two forces, the normal force and the frictional force, that are just in the Y in the case of the normal force and just in the X in the case of the frictional force. So let's do that. That will make our math a little bit simpler. Now let's use Newton's second law and sum up these forces in the X and Y directions. The sum of the forces in the X direction include the frictional force, which is negative because it's pointing in the opposite direction of what we've defined as the positive X direction. And then the weight has an X component, which is going to be pointing in the negative direction, right? If we break this weight down and we can into a little right triangle here, we can see we've got an X component and a Y component. So I'm going to call that weight sub X. And then we've got a positive component of the tension. The tension also has both X and Y components, as you can see. We've got a horizontal component and a vertical component. So I'm going to call this T sub X. And this is all equal to MA. But the acceleration in the X direction is 0 because we're told that the boy is being pulled at a constant speed. So instead of setting this equal to MAX, conveniently we can just set this equal to 0. Now let's sum up the forces in the Y direction. Looking back at our free body diagram, we have the normal force that's just in the Y, and that's positive. And then we have a component of the weight, which is negative. I'll call that W sub y. And then we have another component of the tension that's positive. I'll call that W sub y, or T sub y. And again, when we're summing this up, typically we would set this equal to MAY. That's what Newton's second law tells us to do. But again, we're not accelerating in the y direction. We're not lifting off the surface. We're not burrowing into it. We're not moving at all in the y direction. We're going at a constant, no change in our elevation given the axes that we drew. So there's no acceleration in the y direction, which means, again, conveniently, we get to set this equal to 0. So now we know we can plug things in. These are the two equations that we're dealing with, and when we plug things in, we can start to solve so that we can eventually solve for the tension that shows up here in the x component and the y component. In order to break this down into the x and y components appropriately, let's look at this in a little bit more detail regarding the tension and the weight, because it can be a little bit tricky, particularly for looking at the weight. So here is the weight of the boy. Let's deal with that one first since it's a little bit more tricky. And I'm calling this angle here theta 1. That's the angle that we said is the angle of incline of the hill that's equal to 11 degrees. If we want to break that weight into its x and y components, we can draw something that is parallel to our y-axis and something parallel to our x-axis. And this is going to be our y component. This is going to represent our x component. How do we know what they're equal to in terms of the weight? We need to know this angle. And so what I want to prove now is that that angle I just drew is equal to theta 1, that 11 degrees. If we look at this right here is a right angle. So if this is theta 1 right here, and this is 90 degrees, and we know that the sum of the angles in a triangle are 180, this right here, this angle, must be 90 minus theta 1. Then we know that, again, this whole angle here is a right angle, is 90 degrees. So if this little angle at the top corner of the triangle is 90 minus theta, hey, this angle here must be equal to theta. So that too is theta 1. If that angle is theta 1, then using our trig, we determine that W sub x is going to be W sine theta, because it is the side opposite the angle theta 1. And W sub y is going to be W cosine theta, because it is the side adjacent to the angle theta 1. We can also break the tension down, and luckily that's quite a bit easier. If we look at our tension force, and we break that into a right triangle here, where this is going to be T sub x, and this is going to be T sub y, we can pretty quickly see that T sub x is going to be T cosine theta, since that's the side adjacent to theta 2, and T sub y is T sine theta 2, since that's the side opposite the angle theta 2. Now let's bring these four pieces of information back to the main problem. Here are the equations that we determined from using Newton's second law in our free body diagram. Let's go ahead and substitute in what we know are the x and y components of the weight and the x and y components of the tension. In that first equation, we have the negative frictional force minus the weight times the sine of theta 1, that 11 degrees, plus the tension times the cosine of theta 2, that 40 degrees. In our second equation, we have the normal force minus the weight times the cosine of theta 1, plus the tension times the sine of theta 2. Both of those are equal to 0. And then we also know that we have Some little equations that can help us here. We know what the force of friction is equal to, and we know what the weight is equal to. The force of friction is equal to mu k times N, and we know that the weight is equal to mg. If we plug those in, we're going to get really close to being able to solve for this. Our tension, T, the tension in the rope, that's our ultimate goal here. Here are our equations with those small little mini equations for the force of friction and the weight plugged in. Let's look at what we've got. We know the coefficient of friction, mu, we're given that, right? We don't know the normal force. We do know the mass of the boy. We know g, that constant. We know that angle. Tension is what we're trying to solve for, and we do know this angle theta 2. So you can see that in this first equation, we have two unknowns. We don't know this normal force, and of course we don't know the tension. That's what we're trying to solve for. In the second equation, again, we don't know the normal force. We know m, we know g, we know theta 1. There's the tension we're looking for, and we know theta 2. So again, we have the two same unknowns, n and t. So it looks like we're going to have a system of equations where we have two equations and two unknowns. Let's plug in our numbers and see what these equations look like, cleaned up, and then look at what's the best way to solve them. Here are those same equations with our numbers plugged in. You'll notice we had the mass of the boy is 30, and then we set g equal to 9.81, and then we were careful not to mix up our angles. This is the angle of incline, 11, appearing in both of those equations, and the angle that the rope is being pulled, which is 40 degrees. And then of course we have that coefficient of kinetic friction. Let's actually calculate everything we can, so this is as simplified as possible. Here we've multiplied everything through. If you haven't gotten these same numbers, make sure that you have your calculator in degrees and not radians, since we are using 11 degrees and 40 degrees and not values of radians. Now we need to solve, and again we see, as I pointed out before, that we have two unknowns, this n and this t. And the t is what we actually want to solve for, so we'd like to get rid of that n. As you probably remember from math class, there are several ways to solve a system of equations. In this particular case, with these particular numbers, I'm going to choose to use the elimination method. What I'm doing here in this section is I'm multiplying our bottom equation by 0.15 so that then this term will cancel out with this term when we add the two equations together. If you look over at this set of equations, I've already done that multiplication. So let's add these equations together now. We're just going to add up each term. So negative 0.15n plus 0.15n is 0. So that's nice. That's what we're trying to do, is cancel out one of our two unknowns. 0.67t plus 0.0965t is going to give us 0.8635t, and that's going to be set equal to 56.16 plus 99.49, which gives us 155.65. So we're now about ready to solve for the tension. With the equation that we have one unknown, and we can solve for it by dividing by that coefficient. So we end up getting that the tension is equal to 180.25 newtons. Let's look at this answer and see if this is reasonable. This is actually a reasonable amount for a person to pull. It doesn't sound like a lot of fun, but it's a perfectly reasonable number. And it's important to do those logic checks at the end of a problem so that if we got that she was pulling that rope with a tension of, let's say, 1 newton, which is significantly less than a pound, or pulling with a tension in that rope of 5,000 newtons, but we could recognize we probably have gone wrong somewhere in the problem. But 180 newtons of tension in that rope is perfectly reasonable, and we're satisfied with our answer.